Sound check one. Okay, good morning. Let's go ahead and get started. We're going to look at practice test 3, which is all about chapter 4. And I've picked out a few questions, but I just want to show you that this is in our OneNote file. So you go to the OneNote link in your Canvas homepage, and you're going to see different tabs. There's a welcome tab, live chats, and ask my instructor questions that I received. So I've printed out the practice test in the live chat section, and you'll have to go to the page for practice test 3. And by the way, the other practice tests for test 1 and 2 are still in here, so you can review them for the final. Of course, they're in my math lab as well. But anyway, if you scroll down, you'll see the whole practice test with some answers, at least one version of the practice test. Of course, when you work it in my math lab, the answers will be a little bit different. But off to the side, I have selected a few items. We'll discuss as many of them as we can get to. And the first one is item number 1. It asks us to find the intervals on which f is increasing and the intervals on which it is decreasing. All right, so this is one of the most fundamental concepts in calculus, and that is that you can tell whether a function is increasing or decreasing by looking at its derivative. Because remember, derivative is actually slope. That's all it is. It's a formula for the slope of a function. And if a slope is positive, if you have positive slope, that we've known from a long time from learning about lines back at the very beginning of algebra, that positive slope means that a line is rising if you read it from left to right, and negative slope would mean that it's falling. So from that concept and from the fact that derivatives are really just a formula for slope, we know that if the derivative of a function f prime is positive greater than 0, then that means that f is increasing. And if f prime is less than 0, that means that f is decreasing. So to determine where a function has intervals that are increasing or decreasing is the same as determining, solving an inequality basically, where the function is greater than or less than 0. So let's take a look at our function here. We're going to use a technique called a sign chart in order to find the intervals where the derivative is positive or negative. So first we have to find the derivative. So if the original function f of x is negative 2 cosine of x minus square root of 3x on the interval from 0 to 2 pi, let's find its derivative. And by the way, one page in our live chat section, I have a summary of derivatives. I'm going to select that page really quick. You can see here where we have the derivative of the cosine is negative sine. Hopefully you've memorized that at this point, but if you haven't, then you need to. All right, so what we're going to do is find the first derivative of f. Okay, the coefficient of the function is going to stay the same, -2. The derivative of cosine of x is negative sine x. Okay, and then we have minus square root of 3 times x. Well, anytime you have a linear term, the term that's x with a coefficient, it's just going to be the coefficient, which makes sense because if this were a line, that would be the slope of the line. Okay, so we have our derivative, and now we're going to, well, just clean it up a little bit. F prime of x equals 2 sine x minus the square root of 3. Okay, so to find where the derivative is positive or negative, we're going to make a sign chart for the derivative, f prime. And so it can only change from positive to negative by going through 0. So we're going to find where the first derivative equals 0 first. So 2 sine x minus the square root of 3. By the way, as I'm talking, if you have any questions about any part, you can always type them into the chat bar. And I also want to remind you to please give the video a thumbs up if you find it helpful, because that'll help other students to find the video later on. Okay, so here we go. So 0 equals 2 sine x minus square root of 3. We're going to add square root of 3 over to the other side. Square root of 3 equals 2 sine x. Okay, so now we're going to divide by 2. Square root of 3 divided by 2 equals sine x. All right, so this involves solving a trig equation. We have to keep in mind that we're talking about, we were given an interval from 0 to 2 pi. So we're going to, I'm just going to draw a little picture here. Or actually, you know what? Let's pull up a nice picture of the unit circle here. Online, you can find any number of pictures of unit circles. Let's go ahead and put one in here since we have the ability to do that. All right, so here's a unit circle, and what we're looking for is any angles x that have a sine of √3/2. So let's go look here. Where do we have a sine of positive √3/2? Well, the sine, remember, is the y. So here we would have a sine of positive √3/2, and here as well. So the two angles, there's no others because the signs are negative in the third and fourth quadrants. So between 0 and 2 pi, we just have two angles, pi over 3 and 2 pi over 3, that have a sine of √3/2. So I'm going to plot pi over 3 and 2 pi over 3. Doesn't matter how you place them as long as they're just in numerical order. Okay, so we have pi over 3 and 2 pi over 3 is where the first derivative equals 0. And now we're going to just test some points in between those values in the first derivative to determine whether we have increasing or decreasing intervals. Positive or negative derivative would mean increasing, decreasing original function. So let's see, what would be, remember we're restricted to 0 to 2 pi too. We're not going to go beyond that. So on each interval, we need to pick a value. So for example, a easy value to work with that's less than pi over 3 might be pi over 4. So maybe on this interval we'll use pi over 4. Between pi over 3 and 2 pi over 3 would be pi, for example. Okay, and between 2 pi over 3 and 2 pi, we have a whole bunch of options, but let's see. Oh wait, that's not pi, excuse me, that's pi over 2 is between pi over 3 and 2 pi over 3. And then pi would be between 2 pi over 3 and 2 pi. Okay, and if you're not sure, you can again refer to the unit circle. You can see what angles are between pi over 3 and 2 pi over 3, for example. You can see pi over 2 there. So, all right. So let's go ahead and evaluate f prime at each of these values. So one reason why I always write the little f prime to the side of my number line when I'm making a sign chart is so that I remember what function I'm plugging into, because sometimes we make a sign chart for f, sometimes we make a sign chart for f prime, and sometimes we make a sign chart for f double prime, the second derivative. All right, so plugging into f prime, we have f prime of pi over 4 equals, and it's going to be 2 times the sine of pi over 4 minus the square root of 3. Okay, so 2 times the sine of the pi over 4. Well, sine of pi over 4 is root 2 over 2. If you double that, you just get root 2. So that's going to be the square root of 2 minus the square root of 3. Now, without even looking at a calculator, what do you think the sign of this would be? Would it be positive or would it be negative? So the answer to that lies in which number is larger, right? So what do you think would give you a larger number, taking the square root of 2 or taking the square root of 3? Well, the square root of 3 is bigger, right? So when we subtract that, this is going to give us a negative number. It doesn't really matter what the number is, just knowing it's negative tells us that on the interval from 0 to pi over 3, we're going to have negative values. All right, now we're going to plug in pi over 2. So we have f prime of pi over 2 equals 2 times the sine of pi over 2 minus the square root of 3. Okay, well, that's 2 times the sine of pi over 2 is 1, you can see on the unit circle there, the y coordinate. 2 times 1 minus square root of 3. All right, well, the square root of 3 I know is less than 2 because square root of 4 is 2. So this is going to be 2 minus a number less than 2. That's going to give us a positive result. So that's going to be positive on that interval. And then lastly, we need to check pi. And to do that one, I think I'm going to move this guy. Actually, I'm going to move him over this way. Having trouble. I'm just going to slide over instead. Okay, so here we go. We're going to find f prime of pi. F prime of pi, we're going to have 2 times the sine of pi minus the square root of 3. Now the sine of pi is 0, right? Let's look right here. Sine of pi is 0. Oops, sorry about that. To answer the question that was asked. All right, the question that was asked was, where is the original function increasing or decreasing? So wherever its first derivative is negative, we're going to have decreasing. And wherever its first derivative is positive, we're going to have increasing. So this function is decreasing on two intervals. The interval from 0 to pi over 3, and the interval from 2 pi over 3 to 2 pi. And then it's increasing on the interval from pi over 3 to 2 pi over 3. Okay, so the general procedure is to take the derivative, set it equal to 0, find where it's 0, set up a sign chart for the first derivative, test points between the zeros to see if you get positives or negatives, and then use the rule that the function decreases when the derivative is negative, increases when the derivative is positive. Again, if you have any questions about this item, feel free to ask in the chat bar. Keep in mind that there's a little bit of a delay, so that's okay. I can always stop and go back to the last question. Okay, so the concept of this increasing, determining where a function's increasing and decreasing is related very much so to the concept of local maximum and minimum of a function. So in this problem, it says they're giving us the derivative, which is nice because we don't have to find it ourselves. And the derivative is all we need to determine where a function's increasing or decreasing. And the reason that's important to a local maxima or local minima is this. So let's pretend that this is our graph, right, of the original function f. So suppose this is f, then what we mean by a local maximum is the top of a hill, right, a peak. So this would be a local max. And then a valley at the bottom would have the local minimum. That would be the y value, the y coordinate at each of those points would be our local max and local min. Local because it's not the absolute top point on the graph or the absolute bottom point. In fact, this graph doesn't have an absolute max or min. It just means that you're changing from where the graph is increasing to decreasing or from decreasing to increasing. So it's when we have a change from increasing to decreasing that we have a local max. And if we have a change from decreasing to increasing, we're going to have a local minimum. So when they tell us use the derivative f prime of x equals x minus 1 times x plus 2 times x plus 5 to determine the local maxima and minima, then we're going to use what's called the first derivative test. We're just going to look for this change in the derivative. It also wants us to find the intervals where the function's increasing and decreasing, but that will kind of happen automatically because we're going to set up a first derivative sign chart to find the local extrema anyway. By the way, you can say local extrema to mean both local maxima and minima. All right, so here we go. If f prime of x is equal to x minus 1 times x plus 2 times x plus 5, okay, remember we would like to set up a sign chart. Uh-oh, my stream is going in and out. I hate it when this happens. So I apologize if the stream is choppy. Sometimes this happens and I can't seem to figure out consistently a reason what's causing it, but let's hope it clears up. I might have to shut down the chat and restart it at some point, but I'm gonna keep going for now. I think maybe I'll try closing a few things here. Okay, I restarted it in the hopes that it will improve. Let's see what happens. You might have had to log back in, and I'm sorry about that. So here we go. We're going to continue with the process of constructing a sign chart for the first derivative. So the first step is to set the derivative equal to 0. And this is a nice factored polynomial, so we can solve it very easily. Either x minus 1 is 0, x plus 2 is 0, or x plus 5 is 0. So that would mean x is 1, -2, or -5. We're going to put those on our sign chart for the first derivative. It does not have to be, you know, an exact scale. Only thing that's important is that they're in the correct numerical order. All right, so this is where we have zeros. So on the top, that's our function values. On the bottom, these are our x values, right? And we just found that the derivative is 0 at 3 different points. Now remember what the derivative being 0 looks like. If you look back at this sample graph I drew, this local maximum would be an example of a point where it would have a horizontal tangent line and you'd have a slope of 0. So these are our potential local maxima and minima here. 1, -2, and negative. And what we need to figure out is if there's a change from increasing to decreasing at those points. So we're going to test some values on each interval. I'm going to test -6, -3, 0, and 2. But you can pick any value on those intervals. Okay. So let's go ahead and plug into the first derivative. And now when we do this, it's really nice that the first derivative is in factored form, because you don't really have to find the exact value, you just need the sign. So for example, if you plug -6 into the first derivative, you have -6 minus 1, which is a negative. So a negative times -6 plus 2 is a negative, times -6 plus 5 is also a negative. And negative times negative times negative, an odd number of negatives gives you a negative. So this is going to be a negative value on the interval up to -5. And then we can continue in this way. Okay, if we plug in -3 for x, what are we going to have here? -3 minus 1 would be a negative. -3 plus 2 would be a negative. And -3 plus 5 would be a positive. So negative times negative times positive equals a positive. All right, and then we're going to plug in 0. 0 is really easy. 0, oh, let me go ahead and fill in our positive to our last interval before I forget. Here we go. Okay, plugging in 0, we're going to get -1 times +2 times +5. Negative times positive, which is a negative. So on this interval, we have negatives between -2 and 1. And then the number 2, if we plug that in, we're going to get a positive. Positive times positive equals positive. So this interval is positive. All right, so we were looking for a couple of things. First, we want to identify any local extrema. So remember, when it changes from decreasing to increasing, that means you're at the bottom of a valley. So we have a local minimum at -5. Then it changes from increasing to decreasing at -2. So you have a local maximum or relative maximum. Those terms are used interchangeably, local and relative. All right, and then at 1, we have changing from decreasing to increasing, so that's going to be a local or a relative minimum as well. So our local minima are going to be at x equals -5 and 1. Now I didn't find what the local minima are yet because that's the function value, but we know where it's located at. We don't actually have the original function, so we can only say where the local minima occur, not actually how big or small they are. All right, and local maxima occurs at only x equals -2. All right, we were also asked where it was increasing and decreasing. So let's start with the increasing intervals. The function f would be increasing where f prime is positive. So that's going to occur between -5 and -2. I'll see how the interval is positive there. But it's also positive from 1 to infinity. Okay, and where is f decreasing? That would be the intervals, the other intervals, from -infinity to -5, and from -2 to 1. Okay, so that's how you work the problem when you're given the derivative. If we had not been given the derivative, we would have to find it ourselves. And then you're going to set the derivative equal to 0, set up a sign chart, look for where you have increasing or decreasing intervals by finding where the derivative is positive or negative by testing points. All right, do you have any questions so far? If so, remember you can type them into the chat bar. All right, the next thing I'd like to talk about, again, I'm hitting the highlights, some of the main topics that are on our test review, is L'Hopital's rule. So L'Hopital's rule, remember, addresses the case where we get certain indeterminate forms. Indeterminate forms like 0 divided by 0 or positive infinity divided by positive infinity. So when you're trying to find a limit and you get one of these indeterminate forms, L'Hopital's rule tells us that as long as it matches one of these indeterminate forms specifically, because there are other indeterminate forms, then we can use L'Hopital's rule. Limit as x goes to a of f of x over g of x is equal to the limit as x goes to a of f prime of x over g prime of x. So we can take the derivative and hopefully we'll find that when we go to evaluate the limit, we no longer get an indeterminate form. Or if we do, that we get one of these two indeterminate forms so we can apply it a second time. Okay, so with that in mind, let's look at this problem here. Okay, this one asks us to evaluate the limit, use L'Hopital's rule when it's convenient and applicable. Do you happen to recognize that expression 1 plus a number over x to the x power from anything? Does it look familiar? So you may have seen in college algebra or pre-calculus, you may have seen continuous compounded interest and regular interest. And in the regular interest formula, regular compound interest formula, this expression comes up. And then the two are related, the compound interest and the continuous compound interest, because if you imagine compounding the interest an infinite number of times per year, you end up with e to the x. So in other words, this expression, the limit as x goes to infinity of 1 plus a over x to the x, it looks something like it would end up having an e in it. So let's see what kind of a form we have right now. This is, if you tried to plug in infinity, if you can think of it that way, right? So what would it be to have 1 plus a over infinity to the infinity power? All right, so it looks like this term would go to 0. And so you'd have something of 1 to the infinity power. This is also an indeterminate form. Unfortunately, we don't have a rule for that form. So we have a little bit of work to do to try to get this into a form where we can take the derivative. Or sorry, apply L'Hopital's rule, hopefully. Okay, so this is indeterminate. So now we're going to do a little trick here. We're going to say, okay, we're looking for some number y that's equal to the limit as x goes to infinity of 1 plus a over x. Ooh, that looks pretty bad. Hold on. 1 plus a over x raised to the x power. Okay, so y is what we're looking for. We can't find this. Oh wait, hold on 1 second. I did the wrong thing. I don't want the y to be the limit. I just want y to be the number. So sorry about that. All right, so if y is equal to 1 plus a over x to the x, and we're trying to find the limit of y, before we do, let's go ahead and take the natural log of both sides. And can you think of why I would take the natural log of both sides? Do you remember a rule when you take the natural log of something raised to a power? The power rule of logarithms says that the natural log of, say, n to the p power is the same as p times the natural log of n. So we can bring that power out front. So what we're going to have is that the natural log of y is equal to x times the natural log of 1 plus a over x. Okay, so this changes the form a lot. And this is helpful because you notice that we've now got a product, right? And what we really want actually is a quotient. We want a function over a function. Well, let me clarify that. So if we were to try to take the limit as x goes to infinity of the natural log of y, that would be the limit as x goes to infinity of x times the natural log of 1 plus a over x. Okay, let's see if this is still an indeterminate form. So x would be going to infinity, and then again this guy here would be going to 0, a over a large number is close to 0. And the natural log of 1 would be 0. So you'd have infinity times 0, which is also an indeterminate form, but again, not one that you can use L'Hopital's rule for. Okay, so how can we get it in the form that we want? Well, whenever you have it as a product of infinity times 0, you are in good shape, because instead of writing it as a product, you can write it as a quotient and fix your problem. So what I mean by that is this is the same as the limit as x goes to infinity of, instead of x multiplied by natural log, we could write it as natural log divided by the reciprocal of x. Right? Isn't it true that if you flipped over that 1 over x and multiplied it, you'd end up with the same thing we started with? So in this case, we would have that the denominator, if we tried to plug in infinity, would go to 0, and the numerator would go to 0 as well. So this is also an indeterminate form, but it's one where we can use L'Hopital's rule. L'(H) is my abbreviation for L'Hopital's rule. Okay, so we have that the limit as x goes to infinity of the natural log of y is equal to this. So we're going to apply L'Hopital's rule. What does L'Hopital's rule say? It says take the derivative. All right, so how do we take the derivative of the natural log? So let's go back to our derivative page and just remind you that over here we have the derivative of the natural log of x is 1 over x as long as x is greater than 0. Okay, now this guy is going to have a chain rule involved, and in particular in both the denominator and the numerator we're going to end up having to take the derivative of either 1 over x or a over x. So let's do that off to the side real quick. So we're going to take the derivative with respect to x of 1 over x. Remember, that's the derivative with respect to x of x to the negative 1 power. So you would bring the power up front and subtract 1 from it. So that's going to be negative 1 over x squared. Negative x to the negative 2, or in other words, negative 1 over x squared. And if that had been a over x derivative, which we're also going to have to do, no matter what a is, we would get negative a over x squared. Okay, so let's go ahead and say this is going to be equal to the limit as x goes to infinity of the derivative of natural log of 1 plus a over x is 1 over 1 plus a over x times the derivative of 1 plus a over x, which is negative a over x squared, over, and then we have 1 over x, its derivative would be negative 1 over x squared. Okay, so looks like we have a little simplifying to do. Okay, so this is going to be equal to, let's see, in the numerator we can just multiply straight across, right? And then I can flip the other one up. So we're going to have negative a over x squared times 1 plus a over x. And then flipping the negative 1 over x squared up, it's going to be times negative x squared. Okay, let's see what we need to do with this guy. So we're going to have ax squared over, I'm going to go ahead and distribute the x squared, one of the x's from the x squared. It's going to give me x times x plus a. Then I'm going to cancel one of the x's, and we're going to have ax over x plus a. Okay, oops, I did something that I don't recommend you do, which is I stopped writing my limit, and we don't want to forget that we're taking the limit. So make sure to keep writing your limit. Limit as x goes to infinity. Okay, so we're still taking the limit as x goes to infinity. Hold on one second. Okay, sorry about that. So limit as x goes to infinity of ax over x plus a. Oh, welcome, Cody. Thanks for checking in. All right, so whenever you have a rational function and you're taking the limit to infinity, we say the highest powers dominate. So what that means is we only need to look at the x terms, not the ones that don't have x's. So this is going to be the same as taking the limit as x goes to infinity of ax over x, which is going to just be the same as a. Okay, so what that means is, remember, we were evaluating this limit here, and we just got a. So we just found that the limit as x approaches infinity of the natural log of y is actually equal to just a. But remember, we're trying to find the limit as x goes to infinity of y itself. So we have a little bit more work to do. We just found the limit of the natural log of y. So let's come over here, write down what we found. Sorry, it's got a little less room than I needed. So we're going to have the limit as x goes to infinity of the natural log of y turned out to equal a. What we want is the limit as x goes to infinity of y. Well, there is a property of limits that says you can bring that limit inside of a natural log. So we have the natural log of the limit as x goes to infinity of y equals a. All right, and now to get this guy out of the natural log, we just have to change this from logarithmic notation to exponential notation. Just in case you're rusty on that, remember natural log is log base e. Okay, so what that means is what power do you raise e to get that limit? It's the a power. So e to the a is equal to the limit as x goes to infinity of y. And remember, y was the expression we were working with to begin with. So we just found the limit is e to the a. And as I mentioned at the beginning, I expected it to have an e in there because I knew that it looked like the compound interest formula taken to an infinite number of compounding periods. All right, so that was item number 3 on your review. Please don't hesitate to ask me questions and just type in the chat bar if there's anything you need me to go over. Okay, I can always go back to a previous problem as well. Okay, so the next thing that we're going to look at is number 5. I know that's kind of small. Let me see. Let me make it a little bit bigger. Okay, this one involves writing a linear approximation. Write the equation of the line that represents a linear approximation to the following function at the given point A. Then use the linear approximation to estimate the given quantity and compute the percent error in the approximation, which is 100 times approximation minus exact over exact, where the exact value is given by a calculator. Okay. So first, let's start with write the equation of the line that represents the linear approximation. All right, so on a different page of our OneNote file, right underneath our practice test, I have this information about linear approximations. Okay, so given a function f of x, we can represent its tangent at x equals a. the equation of the tangent line would be L of x equals f of a plus f prime of a times x minus a. By the way, you can get this formula by using the point slope formula for a line. Remember, f prime of a is actually the slope, so you have your slope and you have a point on the line, and you can get this equation yourself. But in any case, this is the equation of the tangent line, and it gives us an approximation for the function, because look, if you look at the graph of the function and the tangent line, you see how close they are? So if there was some x value here, and it was hard for me for some reason to find f of x, I could find L of x instead, and I would know that I'm pretty close to the actual y value at that point. Okay, so that's the idea of a linear approximation. So we're going to go ahead and use this formula here. L of x equals f of a hold on one second. L of x equals f of a plus f prime of a times x minus a. F of 0, so let's do that. F of 0 is going to be 125 of x before we can find f prime of 0. So I need to take the derivative of f of x. So this is going to be a power rule problem. So that's going to bring the power out front, negative 1/3 times, keep the base the same, 125 plus x. We're going to subtract 1 from the exponent, so that's going to be negative 4/3. And then we're going to multiply times the derivative of 125 plus x, which is just 1. Okay. And so that's f prime of x. And we want to know f prime of 0. So f prime of 0 is going to be negative 1/3 times 125 to the negative 4/3 times 1, but we don't need that. And then, so that's going to be negative 1/3 times, and that's going to be 1 over 125 to the 4/3. All right, well, negative 1/3 times, let's see, 125 to the 4/3 is the cubed root of 125, which is 5, raised to the 4th power, which is going to be 625, I believe. Oops, I forgot my 1/3 here. Okay, so we're going to have negative 1/3 times 1 over 625. So let's bring up a calculator here. We have 625 times 3. It's going to be 1825. So that's going to be negative 1 over 1825. Okay, so far what we've done is we determined that our line, our linear approximation at A is in this form. And now we just figured out the two values we needed. F of 0 was 1/5. So we have L of x equals 1/5. Plus we have f prime of 0, which is negative 1 over 1825 times x. Weird looking line, right? Okay. And now we're going to approximate the value of f at 0.1 by plugging it into L. Okay, so now we have our linear approximation, which I think was part A, is that right? A, write the equation of the line. Yeah, we've got, that's part A right there. Okay, now part B, we're going to estimate f of 0.1. Okay, and I'm going to actually write it as f of 1/10 since we have fractions in L. So f of 1/10 is approximately L of 1/10 because 1/10 is very close to 0. And so we have approximately 1/5 minus 1 over 18250, right? Because if you multiply, well, let me just go ahead and write it out. So that would be times 1/10. So we have approximately 1/5 minus 1 over 18250. Okay. So let's go ahead and get a common denominator. So 18250 divided by 5 is equal to 3650. So that means that this is approximately 3650 minus 1 over 18250, getting a common denominator. So we are approximately 3649 over 18250. And I want to say that they wanted it in as a decimal. Let me see what they gave as their answer. Yeah, so for part B, round to the nearest hundredth as needed. Okay, so let's divide that out. So we have 3649 divided by 18250 is approximately 0.20. Okay, so that's part B. And then part C, they want us to compute the percent error in the approximation, which is 100 times the approximation minus the exact over the exact. So what we're going to do is we're going to find the exact value of f of 0.1 using our calculator, plugging into the actual function, and we'll see how close we got, basically. All right. So before I slide the screen over to have more room, let's go ahead and figure out what, according to our calculator, and let's see how many decimal places they want on this. They want 7 decimal places. Don't round until the final answer. Okay. All right, so f of 0.1 is going to be 125.1 to the negative 1/3 power. And you can actually just plug that into your calculator. There's a power button somewhere. It looks like X to the Y, or it looks like a little caret symbol. So, but you're going to need parentheses around your exponent. You would have negative 1/3. All right, so let me see if my calculator do this. All right, so we have 125 raised to the power, parenthesis, of negative 1. Oop, that didn't work. Hold on. 125.1 raised to the power, parenthesis, of 1 negative, that's better, divided by 3. Close parenthesis, equals. Okay, so here is the value. I'm going to write down the first few digits, but I'm going to save that on my calculator there. Come on, calculator. There we go. Gotta move it out of the way. All right. All right, so what you get on your calculator is approximately 0.1999466, etc. All right, so that's going to be as close to exact as we can get. And so the number they're looking for is, for part C, 100 times approximation minus exact. So for part C, we have that value that we just found is our exact value. Okay, so I'm going to save that to the memory of my calculator, and I'm going to take my approximation 0.20 minus, and I'm going to recall that number, equals, and then I'm going to divide by, and I'm going to recall that number again, equals. And we get, this is scientific notation here, so we have to move the decimal place 4 places to the left. And we should get what they had. Let's see if it matches up with the answer in my math lab. Gonna move this over. Sorry, my computer is updating here. Doesn't want to move the screen. There we go. Okay, so there's that. Oh, and then, I'm sorry, I forgot. We're supposed to multiply that by 100. That's still not going to work, though. I must have hit something wrong in my calculator. Hold on. Oh, I know what. No, that's not right. That's not true. Okay, approximation minus exact over exact. 0.20 minus the exact equals that divided by the exact equals, getting a different value than they got. Which is weird. Sorry about that, guys. I don't want to waste too much time on it because this is a fairly minor point. But I'll send out an email afterwards and explain if I can find why my answer is different. Okay. I know we got our approximation. Our approximation looks good, because the real value is 0.1999466. I'm wondering if when they did it, they didn't use the 0.20, but used the expanded form of that, the original not rounded form. That's a possibility. But I'll follow up with you. But anyway, you can see that either way, if we did it our way or my way, it's very close to the original, to the actual value as well. Okay, so moving on. Let me see what we were going to do next. All right, next we're going to do number 6. And it says determine the following indefinite integral. Check your work by differentiating. So this is integration, which is reversing the process of taking the derivative. So whenever you see that you have a radical in an integral or derivative situation, you want to rewrite it as a power. So we're going to take the integral of r to the 13/15 dr, and that way you can address it as a power rule. So you remember the derivative of x to the n with respect to x is n times x to the n minus 1. The integral of x to the n dx, you have to reverse the process. So instead of bringing the power up front and subtracting 1 from it, you're going to divide by the power. You're going to add 1 to the power first and then divide by it. So you're going to have x to the n plus 1 over n plus 1. Okay, and so here in the r version, we need to add 1 to the exponent and divide by it. That's all we have to do. So we're going to have r to the 13/15 plus 1 over 13/15 plus 1. Well, 13/15 plus 1 is going to be 13 plus 15 over 15. So we're going to have 28/15. Oh, and plus c, because remember when we go from the derivative back to the original function, there's a whole family of functions that have that same derivative, and they just differ by a constant. All right, so this is going to be r to the 28/15 over 28/15, or that would be that would be 15 r to the 28/15 over 28 plus c. Okay, now it says check your work by differentiation, because integration and differentiation reverse each other. So we're going to take this function here. So if f of r is equal to 15r to the 28/15 over 28, we're going to find, plus c, we're going to find its derivative. So f prime of r, then we're going to keep the 15/28 the same. We're going to bring the 28/15 out front and subtract 1 from it. And the derivative of a constant is 0. So that gives us f prime of r equals, that's going to be, this cancels all out, that's all going to be 1, r to the 28/15, oh sorry, not 28/15. When we subtract the 1, it's going to become 28/15 minus 15/15, or 13/15, which is what we started with in our original integrand. The stuff here is called the integrand. Okay, and if you get that back, then you know that you integrated correctly. All right. Okay, next problem. All right, so this is related to the problem we just did, because we have to set up an integral for this one ourselves. It says find the solution of the following initial value problem. So what that means is they're giving us the derivative of the original function. You integrate the derivative with respect to x to get something close to g. What I mean is you're going to have g of x plus some number c. You won't know what the constant c is, but you can use this fact that g of 1 is equal to 2 to find c. Okay, so let's go ahead and set up our integral. When we do that, it's going to be easier if we just go ahead and distribute this, because there's no product rule for integration. So I'm going to go ahead and say the integral of, that's going to be 5x to the 5th minus 5x times 1/5 is just going to be x dx. Make sure you're writing your integral and your dx each time. until you apply the rules for integration. So I'm going to now apply the power rule here and here, actually. Think of this as x to the first. So we're going to have 5 stays the same, x to the 6th over 6th minus x squared over 2 plus c. All right, so this is our function g of x with that unknown c in it. So we just found that g of x is equal to 5/6 x to the 6th minus 1/2 x squared plus c. And we know that g of 1 is equal to 2. So what is g of 1 equal to? Well, g of 1 is equal to 5/6, 1 to the 6 is just 1, minus 1/2, 1 squared is just 1, plus c. And if g of 1 is equal to 2, that means 2 is equal to 5/6, let's see, minus 3/6 is 2/6 plus c. Well, that's just 1/3 actually. And then subtracting, let's see, 4/3, I'm sorry, is that right? 6/3 minus 1/3 is going to be 5/3. So c is equal to 5/3. So now we know the function completely. I can erase the c here, and I can put in 5/3 instead. So just by knowing that one point on the original function, and that makes sense, right? Because the derivative tells you the shape of the function, but not its position in the plane. So if you know even one point that it goes through, and you know its shape, then you know the function. Okay. Next, let's look at, I wanted to show you this question because I think people might overcomplicate it. It says, consider the following function and express the relationship between a small change in x and the corresponding change y in the form dy equals f prime of x dx. Okay, so really what are they asking you to do here? They're asking you to fill in the blank with f prime of x, that's it. So they're really just asking you to find a derivative. They're trying to point out that because dy dx is equal to f prime of x, that it's true that dy is f prime of x times dx. Okay, so, and again, what that represents, small change in y, small change in f prime of x dx, and small change in x. Okay, so we're going to find f prime of x. Remember right here I have the cheat sheet for the derivatives, and we're finding the derivative of the, what was it, the cotangent? So derivative of cotangent is negative cosecant squared. So that's going to be, but it's a chain rule problem. So the derivative with respect to x of cotangent of 7x is going to be negative cosecant squared of 7x times the derivative of 7x, which is 7. It's a chain rule because it's not just the cotangent of x, it's cotangent of some function of x. Okay, so that means that your final answer, you would put negative 7 cosecant squared of 7x. All right, so one of the easier problems on the test if you understand what they're asking you to do. Okay, another topic that you need to be very familiar with in this section is concavity, determining where a function is concave up, like it could hold water, or concave down, like water would pour out of it. So again, concave up can look like this or this, and concave down can look like this or this, right? So how do you know when a function is concave up or concave down? Well, the answer to that question lies in the slopes, as calculus could have just been called the study of slopes, right? everything's about slope. So notice that if I take tangent lines along a curve that's concave up and I look at them from left to right, we start with negative values, go through 0, and end up with positive values. The slopes are increasing. Okay. In other words, the derivative is increasing. And similarly, f prime, or the derivative's decreasing if you look at the tangent lines on concave down. So what that means is if we take the derivative of the derivative, then we would have a positive value, right? The derivative of an increasing function is positive. The derivative of a decreasing function is negative. So in general, if f is concave up, that means that f prime is increasing, which means that f double prime is positive. And if f is concave down, that means f prime is decreasing, which means f double prime is negative. And the reverse is true. If you know f double prime is positive, that means f is increasing, which means, f prime is increasing, which means f is concave up. So all we have to do is make a sign chart. When we want concavity, you have to make a sign chart for the second derivative. Okay, so let's get to work finding our second derivative. So we were given the function f of x equals negative natural log of 5x squared plus 7. Remember that the derivative of natural log of x is 1 over x. We already looked at that once today. And in this case, it's going to involve a chain rule because it's not just natural log of x, it's natural log of a function. So we're going to say f prime of x is, the negative tags along, it's going to be 1 over 5x squared plus 7 times the derivative of 5x squared plus 7, which is 10x. So we have negative 10x over 5x squared plus 7. All right, that's the first derivative. Now we have to use the quotient rule to get the second derivative. So do you remember the quotient rule? Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Okay, so let's try this. So bottom would be 5x squared plus 7. Derivative of the top would just be negative 10 minus the top is negative 10x times the derivative of the bottom, which would be 10x, right? Bring the power out front of the x squared. 2 times 5 is 10, and then subtract 1 from it, and you just get an x. Over 5x squared plus 7 squared. Okay, so let's clean this up a little bit before we try to set up a sign chart for f double prime. Oops. All right, so let's see. That's going to be, I'm going to factor out a 10. Is that all I can factor out? Yeah, I can factor out a 10 from the top. Actually, let's just make it a negative 10. That'll be easier to look at, I think. All right, so we're going to take out that negative 10 and that negative 10. And what's left behind is 5x squared plus 7 minus the positive 10x squared over 5x squared plus 7 squared. Okay, so that is going to be negative 10 times 7 minus 5x squared over 5x squared plus 7 quantity squared. Okay, Just want to check how they want your answer given over here. Okay. All right. So how on earth do we set up a sign chart for this function here? Well, remember that when you set up a sign chart, what you're looking for is places where the function is equal to 0. In this case, where the second derivative is equal to 0, or where it's undefined, because those are the places where the values can change from positive to negative. So in order for a rational function, one that looks like a fraction, to be equal to 0, that would mean that its numerator would equal 0. And the only way this numerator could equal 0 is if 7 minus 5x squared is equal to 0. So let's go ahead and solve this guy. So that's going to give us, let's see, x squared equals, subtracting 7 divided by negative 5, 7/5. So we're going to have, by the square root property, x is plus or minus the square root of 7/5. Now we don't like to leave a radical in the denominator. We don't like to leave a fraction under a radical. So we would rationalize this by multiplying by square root of 5 over square root of 5. So you'd actually have x equals plus or minus the square root of 35 over 5. Okay, now to find where it's undefined, to find where f double prime is undefined, you have to set the denominator 5x squared plus 7 equal to 0, and that's not going to have any real solutions, because notice if you multiply a positive x squared times a positive 5 and add 7, you're going to get something bigger than 0. So no real solutions. And we're only talking about real valued functions, so we can disregard that. So the only thing we need to put on our number line is negative square root of 35 over 5 and positive square root of 35 over 5. These are where the second derivative is equal to 0. Now, you should always use exact values as much as possible. But you might want to estimate this just so that you can pick values that you know are in the right interval, because we need test values. So let's go ahead and take the square root of 35 and divide it by 5, and that's about 1.2. Okay, so we have approximately negative 1.2 and approximately positive 1.2. So my test points that I'm going to use in between, I'm going to pick 0, I'm going to pick 2, and I'm going to pick negative 2. And we need to plug those into our second derivative and determine the sign. Okay, so looking at our second derivative, which is, remember here, the denominator is always positive because it's a number squared. It's actually a positive number squared. So you can actually disregard the denominator and just look at the sign of the numerator, because the denominator won't affect the sign. So I'm going to find the sign of negative 10 times 7 minus 5 times negative 2 squared. All right, so this is going to be a negative times, and then this is going to be a negative as well, because 5 times 4 is 20, which is bigger than 7. Negative times a negative equals a positive. So I'm going to have positives here. And notice that when I plug in 2, it's going to be the same result. Just, when you square negative 2, it's the same as squaring 2. So this end is going to be positive as well. Now if I plug in 0, I have negative 10 times 7 minus 5 times 0 squared. That's going to be a negative times a positive, so that's going to be negative. All right, so why were we doing this sign chart? Remember, the sign chart for the second derivative is always to determine concavity of the original function. So we have that the original function is f is concave up, like a cup, on the intervals where f double prime is positive. Negative infinity to negative square root of 35 over 5 and square root of 35 over 5 to infinity. And then it's going to be concave down in between from negative square root of 35 over 5 to positive square root of 35 over 5. Okay, so that's how you determine concavity. Remember that you can always let me know if there's anything you have a question about or anything you'd like me to repeat. Okay, so this is the final answer here. All right. Okay, next we're going to look at item number 10 on the review, which is use the derivative f prime to determine the local minima and maxima of f and the intervals of increase and decrease, and sketch a possible graph of f. Okay, so the reason I wanted to work this one is because I think people might be a little confused about what they mean by sketch a possible graph of f. So remember here, the derivative gives us the shape of the function, but it doesn't tell us where it's located in the plane. So I don't know the original function f. I know what it would look like if I integrated this. I could get what f looks like, but there would be still a constant that I didn't know. So all this question is asking you to do is to draw a graph that would increase and decrease on the same intervals that f does. So we're going to analyze the first derivative with a sign chart. Make a first derivative sign chart. And that's going to tell us where the original function is increasing, decreasing, and has these local extrema. So f prime, okay, we're going to need to know where it equals 0 or is undefined, but sine of 3x is never undefined. So we're just going to say, where does 9 sine 3x equal 0? Again, I'm setting the first derivative to 0. All right, so dividing by 9, we get that the sine of 3x is equal to 0. Okay, and how do you solve a trig equation like this one? Where do we have the sine of 3x equals 0? Well, that depends on what domain we're looking at. So they told us that our domain is negative 4 pi over 3 to 4 pi over 3. That means that all of our x values have to be between negative 4 pi over 3 and 4 pi over 3. But to solve this trig equation, we actually have to solve for 3x. So what we're going to do is multiply through by 3 on all sides of this inequality. And that's going to give us that negative 4 pi is less than or equal to 3x is less than or equal to 4 pi. So we're going to find any solution, any angle. We're going to call that angle 3x. You could think of it as like alpha or something if you don't like the 3x being there. But anyway, any angle between negative 4 pi and positive 4 pi that has a sine of 0. Okay, so let's go ahead and grab that. Well, maybe not this time. what has signs of 0 on your unit circle? So let's draw our unit circle here. Okay, this would be, oops, that's not a circle. Okay, so let's say that this is our unit circle. Okay, so we're going to have the sign, remember, is the y value. Y is up and down. So for the sign to be 0 would mean that we're on the x-axis, right? That's where we have y coordinates of 0. So if we're going from negative 4 pi to 4 pi, well, let's start with 0 and go to 4 pi, and then we'll go back the other way. So we're going to have the x value 0, or the angle 0, I should say. And then we're going to go over here and we'll have the angle pi. And then we'll go around here and we'll have the angle 2 pi. We'll go around again and we'll have the angle 3 pi. We'll go around again and we'll have the angle 4 pi. And 4 pi is included because it's an or equal to situation. All right, going back the other way, you'd have the negative versions of all those angles, right? You have 0, then we go negative pi, negative 2 pi, negative 3 pi, negative 4 pi. So what we just figured out is that the solution to this equation is that 3x can be negative 4 pi, negative 3 pi, negative 2 pi, negative pi, 0, pi, 2 pi, 3 pi, and 4 pi. Okay, that's what 3x is equal to. And so what is x equal to? X is equal to negative 4 pi over 3, right? Divide by 3. Negative pi, if you divide negative 3 pi by 3. Negative 2 pi over 3. Negative pi over 3, 0, pi over 3, 2 pi over 3, 3 pi divided by 3 is just pi, and 4 pi over 3. Wow, I might need a longer sign chart here. That's a lot of values. Okay. Okay, so let me adjust my sign chart. So f prime of x is equal to, or not is equal to, but is on this sign chart here. Yeah, I might need more room even than that. Hold on. Okay, so this is going to be my f prime sign chart, and we're going to have negative 4 pi over 3, negative pi, negative 2 pi over 3, negative pi over 3, 0, pi over 3, 2 pi over 3, pi, and 4 pi over 3. Okay. All right, so now we want to find the intervals on which this is increasing or decreasing. So I'm trying to think if there's a faster way to do this. Let's see. Let's grab the unit circle. Okay, let's talk about what we see. All right. So let's do the positive side first, starting from 0 to pi over 3, for example. So from 0 to pi over 3, let's see, wait. We're plugging into sine of 3x. Just trying to think of the easiest way to explain this. Hold on one second. So I'm thinking two different things here, and I'm going to mention them both just in case it's easier for you to think about. All right, since we're talking about the first derivative is 9 times the sine of 3x, it's like taking 9 times the sine of, instead of the values that are here, 3 times those values, right? So we're losing these denominators. So my point is you can think back to this list, and you can think back to the unit circle that we did here, and you can say, okay, so when x is, say, between 0 and pi over 3, that means 3x is between 0 and pi. And between 0 and pi, all of the y values are the sine values, and they're all positive. So between 0 and pi over 3, then, we must have positive values of the derivative. Okay, the longer version of that, the alternative would be on that same interval, instead of looking at, the values of 3x, to actually plug in some kind of value between 0 and pi over 3, like pi over 6, for example. All right, so if you take the sine of 3 times pi over 6 and multiply it by 9, then we want to see what whether it's positive or negative, right? So this is going to be 9 times the sine of pi over 2. Well, pi over 2 has a sine of 1, right? So that means that's just 9, which is positive. So we would get positive that way as well. Okay, but working it out, plugging in, trying to find something on each interval is going to take a while. So I'm going to go by my previous thought, which is I'm going to think about the values of 3x and how they look on the unit circle. So, oops. Okay, so what I'm going to do is, where's my blue? Okay. All right, so if we said from 0 to pi over 3, that means that that corresponds to 0 to pi on the regular unit circle. We have all positives. Then from pi over 3 to 2 pi over 3, that corresponds to pi to 2 pi, which has all negatives. So that's going to be negative. And then from 2 pi over 3 to pi, we're going to be like going 2 pi to 3 pi, which is in the top again. So that's going to be positives. And then going from pi to 4 pi over 3 is like going from 3 pi to 4 pi, which is going to be in the bottom again, which is going to be negatives. And you can see that it's going to repeat, right? We know how sine functions work, so we can conclude this is just going to keep rotating through, alternating, right? Okay, so there is our sine chart. So we have a function that decreases, then increases, then decreases, and increases, and so on. But what we don't know is what it actually looks like, where it's actually located in the plane. But they've asked us to draw an example of a function that it could be. And so what we're going to do is we're going to mark off Each of these is going to be worth pi over 3. So we have pi over 3, 2 pi over 3, pi, 4 pi, pi over 3, 2 pi over 3, negative pi, negative 4 pi over 3. All right, so each one of these is a place where the derivative is 0, which means it's a relative max or min. At negative 4/3 pi, we're going from, let me call your attention up here to the sign chart. At negative 4/3 pi, we're changing from negative to positive, which means if the derivative's changing from negative to positive, the original function changes from decreasing to increasing. All right, so let's, we also know that, by the way, the sine function oscillates between 1 and, well, that's not true either. But we do know that trig functions oscillate, and we generally have some value that's our amplitude. Most likely that's going to be 9 to negative 9. But in any case, we're going to, oops, that would be more like here. All right, so if we're going to change from decreasing to increasing at negative 4/3 pi, then it's got to be that it was down at the bottommost point of the function, right? And then it turns around and increases. And then it increases up until we get to negative pi, where it turns around again. And so at each one of these points, it's going to jump back and forth between a and negative a. And so we're going to have a graph that looks, oh, this looks pretty bad. I'm having trouble because I drew them too close together. So let me just draw them a little differently. Okay, so I'm gonna make it twice as spread out here. All right, so here's negative pi, and here's pi. We have some kind of amplitude, a to negative a. It's possible, of course, that this is not centered at the x-axis. We don't know where it's positioned in the coordinate system. This is just an example of a graph that would have this shape. And so we were down here, and then up, and then down, and then up, and then down, and then up, and then down, and then up. All right, so it's going to be, it's a little hard to draw smoothly with this ink tool, but hold on. Okay, maybe if I start in the middle. Okay. Hopefully you get the idea. Okay, so it's going to be a function that is oscillating, of course, because it's a trig function. All right, so again, if you have any, this would be a possible graph of f. right? It's possible that the whole graph is shifted up or down depending on what constant was added to it to begin with, but we weren't given that information. Okay. Okay, we'll do one more problem and then I'm going to stop for today. So this one, we haven't touched on absolute extreme values. So I want to mention that whenever you're asked to find the absolute extreme values of a function, you're either looking for the very top of the function or very bottom of the function if there's no limit on the domain. So for example, if I gave you y equals x squared, we know the graph of y equals x squared, it has a vertex which is the absolute lowest point on the function. This is an absolute minimum. There is no other y value lower than that. So this has an absolute minimum at x equals 0. The absolute minimum is y equals 0. Whenever I say where does it occur, I'm talking about x. Whatever I say what is the minimum, I'm talking about y. All right, but most functions don't, or a lot of functions don't have an absolute minimum, like y equals x cubed, right? It goes up forever and down forever. It doesn't have an absolute max or an absolute min, no absolute extrema. But if you restrict it to a closed interval, a domain, a restricted domain, then suddenly it does, at the endpoints, have both an absolute maximum and an absolute minimum value. And that's the case with all continuous functions. If you restrict it to a closed interval, you'll either have a low point or high point, like we did in x squared, or you know, where the graph changes from increasing to decreasing, or if that doesn't happen, you at least have a highest or lowest value at the endpoints. So what I'm saying is that the absolute extreme values always occur either at critical values, which means values where the derivative is 0, or endpoints, as long as the function is continuous. And every polynomial function is continuous, so we don't have to worry about the possibility of contradicting this with an asymptote somewhere. So let's go ahead then and find the absolute extreme values by finding the critical values first. So that just means setting the first derivative equal to 0. And then we're going to plug the n, and by the way, we're only looking for critical values on the interval from -8 to 1. So I have to remember that. And then we're going to plug those values in and the endpoints in and see which is the biggest and which is the smallest, and those have to be the absolute max and min. So using the power rule here for taking the derivative of x cubed, we're going to bring the 3 out front and subtract 1. So we're going to have 8/3 times 3x squared plus 26 times, again, power rule, bring the 2 out front, subtract 1 from it, so we get 2x, minus the derivative of 28x is just 28. Let's clean this up a little bit. So f prime of x equals 8x squared plus 52x minus 28. And we want to find the critical values, which is where the derivative is equal to 0. So we need to solve this equation. Let's go ahead and divide through by 4 though on both sides, because that'll make our numbers a little smaller. We'll have 2x squared plus 26x minus 7 equals 0. Okay, now you can use factoring or the quadratic formula to solve for x. I think I'm going to use the quadratic formula. So x is equal to, and we're going to have negative 26 plus or minus the square root of, so that's negative b plus or minus b squared, so 26 squared minus 4 times a times c, all over 2 times a. All right, make sure to be careful with your order of operations here. See, we're gonna have 26 squared minus parenthesis 4 times 2 times negative 7, close parenthesis, equals, so we have 732 under the radical, which I do not believe is a perfect square, no. So that's going to be negative 26 plus or minus the square root of 732 all over 4. I'm just trying to simplify the 732 here. So, oop, lost my pen. So 2 goes into 732, 366, 2 goes into 366, 183, 3 goes into 183, 61, and I think 61's prime. So this is going to be negative 26 plus or minus the square root of 2 squared times 3 times 61, all over 4. So that's negative 26 plus or minus 2 times the square root of 183, all over 4, which reduces to negative 13 plus or minus square root of 183 over 2. Ooh, that's a mess. Hold on just a second. Let me make sure I did this right before we continue. No, I think I made an error somewhere. Let's see. Sorry about that, guys. Can anybody see my error? Checking my arithmetic, hold on. 676 plus 4 times 2 plus 56 equals 732, yeah. Negative 28. Oh, I see the problem. Okay, sorry. I divided by 2 instead of by 4 in my head here. This should have been a 13. Okay. So let's fix our quadratic function here. It's going to be negative 13, and this is going to be negative 13 squared. Okay, so we have negative 13 plus or minus square root 13 squared minus 4 times 2 times negative 7 over 2 times 2. So that will give us something nicer, I think. 13 squared is 169 plus 56 is 225. Much better. All right, so this should have been negative 13 plus or minus the square root of 225 over 4. Square root of 225 is 15. Okay, so that's going to be negative 13 plus or minus 15 over 4. So we either have negative 13 minus 15 is negative 28 over 4, which is negative 7. Or we have negative 13 plus 15 is positive 2 over 4, which is 1/2. Okay, so these are our critical values, CVs, and we want to check those and the endpoints to see what their y values would be. So these are x values, and we're going to plug them into the original function. The original function was up here. I'm going to copy it again down to the bottom. Let's see here. Okay, so I'm oops, that didn't work. There we go. Okay, so here's our original function, and now we know that we want to find f of negative 8. And notice that negative 7 and 1/2 are both in that interval, so we're going to check both of those. F of negative 7, F of 1/2, and F of the other endpoint 1. Okay, so plugging in each of these, let's see what we got. Now let's write it out. Let's see. So we're going to have 8 times negative 8 cubed over 3 plus 26 times negative 8 squared minus 28 times negative 8. So let's see. That's going to be... Come on, pen. That's going to be 4,096 negative over 3. Check my arithmetic, please, if you're watching. Plus, we have 26 times 64 is 1664. Come on, pen. You can do it. There we go, 1664, and then plus 28 times 8 is 224. Okay, let me grab my better calculator, one sec. All right, sorry for the pause there. I've got a calculator to make this much faster. So, all right, so we have negative 4,096 thirds plus 1664 plus 224 is and now I'm going to make it an improper fraction. So this is going to be 1568 over 3, which as a decimal is about 522.7. The only reason I'm making a note of that is because we need to know what the biggest and smallest values of these would be. All right, so f of negative 7 then, we have 8 times negative 7 cubed over 3 plus 26 times negative 7 squared minus 28 times negative 7. All right, let's see what this would be. So we have negative 7 cubed times 8 is going to be negative negative 2744 over 3 plus, we're going to have 49 times 26 is 1274, and then 28 times 7 is 196. So we have 1274 plus 196 plus we have 2744 over 3. Which is 2384 2/3. Which in improper fraction notation, oh, my calculator doesn't like that one. Let's see. It's going to be 3 times 2384 plus 2. 7154 over 3. Okay, and then f of 1/2. It's going to be 8 times 1/2 cubed over 3. Plus 26 times 1/2 squared minus 28 times 1/2. Okay, let's see. That's going to be 1/2 cubed is 1/8 times 8 is 1. So that's going to just be 1/3. And then 26/4, which reduces to 13/2. And then minus half of 28 is 14. So we have 1/3 plus 13/2 minus 14 equals, and switching that to an improper fraction, negative 43/6. And then f of 1 is going to be 8 times 1 cubed over 3 plus 26 times 1 squared minus 28 times 1, which is going to be 8/3 plus 26 minus 28, or 8/3 minus 2. 8/3 minus 6/3 would be 2/3. Okay, so then we have to look and figure out what's the largest value on the list and the smallest value on the list. And actually, I don't think I even need a calculator estimate, because 7154 is bigger than the others. 7154 over 3 is bigger than 2/3 or 1568/3, and then this one is the smallest because it's a negative. So this would be our absolute max, and this would be our absolute min, assuming I did my arithmetic correctly. So I don't want to keep you any longer. The idea of this is to check the critical values and the endpoints, and then just plug them into the original function, and whatever's the biggest is your absolute maximum, whatever's the smallest is your absolute minimum. Okay, I hope that this chat was helpful. If you have other questions that you need help with from the review, don't hesitate to send me your Ask My Instructor questions. I do want to mention that from time to time I've had trouble where the Ask My Instructor questions went to my junk mail. So if you did not get a response to an Ask My Instructor question, please don't be shy about emailing me through Canvas to just say, hey, Ms. Earn, I didn't get a response and I need help. It doesn't bother me. I feel bad when I find those junk emails that I've missed. So even though I check them, sometimes I miss them. So anyway, good luck on your test, and don't be a stranger. I'm here to help you. Have a good weekend.